Alright, howdy y'all. It's the Diabolic vtutor, and we're back with some more problems. It's going to be mixed topics this time, as indicated by the title. So we're going to be covering some random problems, ranging from graphing polynomials, to working with quadratics, to working with radicals and logarithms. So basically past streams coming back in a mixed session. Okay. There we go. Let's just open up the situation with a graphing problem, of course. So let's graph. And we're given some sort of polynomial. So we have b of x. Why is it b of x? I don't know. I should have written as p of x. So we have 4x cubed. That's not going to be too bad. It's just a cubic function. These problems I've written maybe 5 to 7 years ago. So hopefully they're still going to be good. That's the given function. So all we need to do is consider a few things. Can we factor by grouping? I don't think so. These are factors of 2, 2, and then this is going to be 2 times 2 times 3. This is a 5, and this is a 2 times 3. So I don't think we can factor by grouping, or it's not going to be very obvious what the factors are. So rather, I'm just going to default to the generic synthetic equation situation. So factors of 6, 1, 2, 3, and 6. Factors of 4, 1, 2, and 4. We have plus or minus kind of situation. Okay. And of course, doing the cardinal sign, that's one sign change. It's 2 sign changes for the positive. So we have up to 2 positive real solutions. Or 0. And then of course using the negative input to figure out how many negative real solutions we've got. That'll be no sign change, no sign change, 1 sign change. So we are guaranteed 1 negative real solution. And hopefully it's going to be rational. It better be rational, you know. Alright, so this is a cubic function. You're guaranteed to have 1 real solution. In this case, we're guaranteed the negative real solution, so we shall start our guess and check with the negatives. So let's try -1. It's always a classic, right? So do we have all the terms present and accounted for? 3, 2, 1, and 0. Yes. So we shall extract the coefficients. So that's the 4. We have the -12. We have the +5. And we have the +6. So drop that down. 4. -4, -16, doesn't look like it's going to work out after all. That's okay. And -21 right here, so we have -15 as a result, which means that -1 is not a valid 0 of the function. We need something a little different, of course. You can see that the number snowballed a bit, so maybe we'll try -1/2, -1/2 as a potential 0. Copy paste those numbers, of course. 4, -12, 5, and then 6. Drop that down, multiplication. We get that. That's looks okay. Okay, so we have -14, and then we have +7. That is a 12, looks good, and then that gives us a -6, which is exactly what we want, because we're going to get a summation of 0. Perfect. Which means, since this one got a remainder of 0, then this must be a 0, and we can convert it, therefore, into a factor. So just subtract by itself. So x minus -1/2 is plus 1/2. So that is our factor. This quotient is also a polynomial. So we're down taking the exponent because we are dividing out one of these factors. So therefore, this is now exponent 2, and this is exponent 1 for the quotient. And since each of these coefficients is divisible by 2, that's what we're going to do. So dividing by 2 so that we can transfer the factor from those 3 terms to this factor just to beautify it. So factor out the 2, we're going to get 2 times 2x squared minus 7x plus 6. And as stated, we're going to transfer that over to this one just to make it look nice. So 2x plus 1. You don't have to do this. Some people prefer to keep this as exponent. Some people prefer to keep it with coefficient 1, but I like whole numbers inside these factors. So it depends on teacher or your personal preference. So this one itself is a quadratic, of course. We have factors of 2, 1, and then we have factors of 6, 1, probably 2, 3. Yeah, 2, 3. 2 times 3 gives us 6, 2 times 1 gives us 2, which combination can potentially produce a negative 7x in the middle. That's going to be 2x times 2 and 1x times 3. So thus, the 2x has to be multiplied to the 2, so like that, follow that construction. And then the 1x here has to be multiplied to a 3, which has to be right there. And then both signs are the same, both are negative, so negative and negative. Alright, copy paste this 2x plus 1, and we have fully factored form. It's a nice problem. And that is equal to b of x. Let me just do a quick check to make sure I didn't miss anything. Partial check, so this is going to be positive 6 distribution, yes. Partial distribution, we have 4x cubed. 4x cubed, okay. So this is probably good. And now we're going to get to graphing. So let's just jump straight to the graph. So zeros, let me start to colorize a few things. So for this particular factor, the 0 is negative 1/2. For that one, it's going to be, what is that? Rehabs. And lastly, for this one, it's going to be positive 2. I do like color-coding things. But if I'm doing this problem by myself, I wouldn't actually do any color. Alright, so we have a 0 at negative 1/2. So here's negative 1, and here's negative 2. So we have a 0 at negative 1. I mean negative 1/2, I'm sorry, right here. And of course, on the other side, here's positive 1, here's positive 2, here's positive 3. So we have a 0 at 3/2, which is right here. 1 and 1/2, and then we have a 0 at 2, so right there. Sounds good. Let's determine the end behaviors, of course. We have a 4x cubed. It's going to be positive coefficient with an odd leading degree. So basically it's going to be doing the down-up shenanigans, like so. Alright, so here we go. Again, we know that it's going to be going down, and then up for the end behaviors. Because if you cube a negative value, a large size negative value, it's going to be a very large size negative value. It's going to go up. It's going to loop back around. And then it's going to be going down, and then it loops back up, like so. And it goes back up. Because if you cube a large size positive x value, it's going to be a resulting huge size positive y value. Alright, so like I said, like before, I don't like to commit myself to where the loop is located, but I guess I should do it. So let's do it like that. And here's a viewing window. This is where I just usually cut that part off. I'm gonna probably cut this part off as well. Alright, that's it for this particular problem. Pretty simple. It's just a cubic function. It's gonna not be too involved. Why did I circle this? So yeah, nothing too involved. It's just gonna be straightforward cubic function. Down-up behavior, fully factored form. The zeros are pretty nice in this situation, and then now we have them all right here. We're good to go. Alright, first problem down, and then we have problem number 2. We have the graph of c of x. Something random c of x. I don't know why I skipped a of x, but here's c of x. We are given the graph of c of x to the right. So let me... Oh, I unfortunately have to draw this. If only I had pre-planned this. That's okay. Alright, so let's put some hash marks. We have 1, 2, 3, 4, 5. 6, 7, 8, and then 1, 2, 3, 4, negative 5. 6, 7. Nothing beyond that probably. And then positive 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, negative 5. Alright, that should be good enough. And the graph is given 1, 2. So let me colorize this. So we have this particular point right here. It's going to be 1, 2. And then we have point there and point there. What else do we have? We have a movement of 2. Big hint. And then 1, 2, 3, 4 down. So 1, 2, 3, 4 down right here. Hope you remember counting spaces for our parabolas. Again, it's going to be 2 and then down 4. This is not drawn to scale, unfortunately, so the points are a little funky. So something like this. Alright, that's going to have to be good enough. Okay, so we're given, this is c of x. So let me put that c of x. And of course our job is probably to find the equation of g of x, right? The graph of, c of x is given to the right, determine the value of c5. So our job is to figure out what is c5. So what has happened? Well, we're given function c of x, it's a parabola. We are told explicitly, I should probably write that down. Let me write that down. C of x is a parabola. C of x is a quadratic equation. Just to be absolutely clear. Okay. So given that c of x is a quadratic equation, then what is the value of c of 5? So we're not given an explicit formula. We're not given an explicit equation. We are given the graph of the function. Unfortunately, we don't have the graph at the 5 point. It'll be somewhere like way down there. So it's off window. That's perfectly fine. So we have a couple of main strats we can do. We can, number 1, figure out the actual equation for the function, which is what I'm going to be doing. Or you can just count spaces, since this is a very nice parabola, which I would use to check the answer afterwards. So let's just do it by generating the equation first. So this classic vertex. So we can take those values, the value of x. When x is 1, then y value is 2. So we can use that to populate our skeletal equation for c of x. So here we go. C of x is equal to some sort of a coefficient in the front. We don't know what it is, but we know it's going to be negative because it's going downwards. And then we have the, again, skeletal equation. So x minus 1, because it's opposite line inside parentheticals. It's a quadratic, so it's going to be squared. And then we have a 2 for the y value, so it's plus 2. So this is just vertex form, skeletal equation, using the vertex that's given explicitly right there. All right. So at this point, you can be fancy-smancy. You can take 1 point, and then you could just plug them into the xy coordinates right here. So here's what I mean. This point right here, if we colorize... You know what? Let me colorize a few more things. So again, this one came from the vertex, and then this one also came from the vertex. And a few other things. So this point right here is 3, comma 2. So if you don't like counting spaces, which I think is a very strong strat, but if you feel like that's a little shoddy, then you could just simply plug and jug. So if x value is 3, then y value is 2, right? Because that's a point on the function, on the graph of the function. So if you plug in 3 for this one, then the resulting y will be 2. And then we can use that to solve for a. So this one is a slightly more robust than just counting spaces, but again, in my opinion, counting spaces is very strong. So this one simplifies to 2, and then 2 squared is 4. So 4 times a plus 2 is equal to 2. Alright. And then, of course, oh, something weird happened. Something does not look right. What happened? Oh, I'm sorry, this is a negative 2. Whoops. So I said positive 2, but it's going down the y-axis. So this is negative 2. That's a negative 2. That's a negative 2. Okay. So subtract 2 from both sides. We get negative 4 is equal to 4a. Thus, solving for a is equal to negative 1. So we have successfully generated our c of x equation. So therefore, c of x, the actual equation, is going to be negative 1 times x minus 1 squared plus 2. There we go. So now we can take this 5 here and then slam dunk it into our equation. Thereby getting c of 5 is equal to what? Now it just comes the number crunching. So negative x value is 5. Copy paste the rest of this. So 5 minus 1 is 4. 4 squared is 16 with a negative in front. So that's going to be negative 16 plus the 2. So final answer is thus negative 14. And when we are good to go. Alright, but in terms of a few notes, remember we could always do the counting spaces if the graph of the parabola is nice, and it's very nice. Here's the reason why it's nice, because it starts off at the vertex here, and then we have a 1 to negative 1 standard, fairly standard movement, but it's just reflected across. So it's a 1 to 1, it's a 2 to 4, so that's very one coefficient behavior, but since it goes downwards, it's negative. So that's how you can generate the a value straight up without having to do so much calculations. So if you're in like a multiple choice question, or you're like some sort of standardized test, then it pays, you save a little bit of time if you just count spaces. Again, if it's a nicely graphed parabola. Okay. But because we know that the a value is negative 1, regardless of what method you use, if you figured out that the a value is negative 1, you could actually count spaces for the a. Okay, so here's how we can do it. Make note that our vertex is at 1, 2. So in order to get to an x value of 5, you need to move over how many spaces from this x coordinate? You need to move 4 spaces, so 1, 2, 3, and then 4. Because this is a negative 1 movement, the standard movement is 4 squared, which would take us to upwards by 16 spaces, but because it's a negative 1 modification, we go downwards 16 spaces. So minus 16 spaces downwards from the current y height, which is 2. So 2 minus 16 is going to be negative 14. As you see, that takes us directly to this answer right there. So in other words, if you know how to count spaces, and if this is a nice graph, you can just simply count spaces to figure out the a value. It's again 1 to negative 1 movement. And then you can consider how many movements it is from the 1 to the 5 that we desire, which is 4 spaces. So 4 squared is 16, but 16 modified by the negative 1 is negative 16 spaces. That's how we're moving. So 16 spaces down from the starting off value of 2. So you can avoid all this if you wish. Again, if it's like a multiple choice, if this is a question on a free response for your teacher, you should probably show work. Because if you don't show enough work, you're probably going to get deducted points for unfortunate reasons. Alright, but we're done with that one. Our next job is to sketch another graph. We love graphing, right? The next function is going to be g of x. It seems like I've skipped letters. So g of x. This is a graphing situation. So graph. This is technically a complete sentence. So sketch the graph of g of x. Wait a minute, what the heck? The directions say to sketch the graph of d of x, but then I gave g of x. That's odd. Okay, well, doesn't matter. We're going to be given a g of x function, and we're just going to graph it. So inside the brackets, we have negative x cubed times 2 minus x squared. Close the parenthetical, and then square that nonsense, and then raise to the power of 3. Okay, so just be aware, this is strictly a polynomial function. It just looks fancy because of all these parentheticals, brackets, and then all these exponents. But really, you just need to use distributive property of exponents. So it's a good mix of mechanics we've already covered. So this is factor number 1, well, with a negative in front. So this is factor number 1, and then this is factor number 2, multiplicity 2, multiplicity 3. So we can start by simply using distributive property. So distribute this 3 exponent to factor chunk number 1 and then factor chunk number 2. So we're essentially clearing the brackets first by using distributive property for exponents. So we're going to get negative because cubic doesn't eradicate negative signs. And then raise that exponent. So 3 times 3 is 9, and then 3 times 2 is 6. G of x. And that's the main thing I would do. I would not bother distributing this binomial. It's honestly quite a waste, a bit of a waste of time. Alright, so at this point we should get the leading term. We could get that by using partial distribution. You don't need to fully distribute this. So partial distribution, we're going to distribute this 6 exponent partially to this thing. So when we do that, negative raised to 6 power will become positive. And then 6 distributed to this 2 becomes 12. So partial distribution, and we're going to distribute it to this negative x power 9, resulting in a leading term of negative x to the power of 21. So leading term right here. And that's the basis for which we're going to determine the end behaviors for our functions. We have the zeros. We can figure out the zero for this factor and for that factor. Yeah. Oh, wait a minute. This is technically a difference of 2 squares. Okay, well, that causes a little bit of problems. So let's take a step back. This is still going to be the leading term. Okay, so leading term. I'm actually going to do a little bit more. We're going to take this one. We're actually going to factorize this because it's a perfect square number 1. This is not a rational square, but it is a perfect square. So we can factorize this junk into square root of 2 minus x times square root of 2 plus x. And then distributive property of exponent. This gets multiplicity 6, multiplicity 6. Yeah. And then copy paste the first factor. So what that means is that we have 3 distinct zeros. We have a 0 here, we have a 0 there, and then we have a 0 right there. And then we already have the leading term. So we have enough to begin graphing the situation. So x-axis, y-axis. We have a 0 at 0 with a multiplicity 9, so that's a straight pass-through. We have a 0 at positive root 2. What is root 2? Root 2 is between root 1 and root 4. Yeah. Root 1 and root 4, so it's closer to this one. So it's like 1 point something, 1.2-ish. Okay. So right here, we have a 0 at root 2. I'm just going to call this 1 right here. This is 2. Alright. This is negative 1, and then this is negative 2. Okay. So again, the 0, oops, wrong color. So the 0 of this one is root 2, and then the 0 for that one is negative root 2. So again, that's like negative 1.2-ish. So a little bit past negative 1, so like right here-ish. Alright, so we have the 3 unique zeros. Each of those is multiplicity 6. This is multiplicity 9. But let's first deal with the leading term for the end behaviors. Alright, so we have a negative in front. This is an odd multiplicity, so it's not going to be going down up like this. Because there's a reflection, it goes from up, down kind of situation. So from this particular 0, we're going to be going upwards, and then from this particular 0, we're going to be going downwards. And again, multiplicity 6 on this one, and multiplicity 6 on that one. So it's basically going to have a parabolic motif right here, and just make it agree with this end behavior. So we have this upwards, upwards. Again, parabolic motif right here. And just to harmonize the picture, I'm going to move this over just a little bit. Right, so now the end behavior is in agreement with this particular 0. Again, multiplicity 2, even multiplicity, you have the touch and go for right here. And then for this particular 0, it's odd multiplicity, so it's going to be kind of a back turn, and then you go pierce right through this particular 0, like so. Okay, again, hand drawn ain't exactly the best graphs. Have to control Z so many times. Just pierce through like this. Alright, so multiplicity is taken care of, and then this multiplicity is taken care of. We have an even multiplicity on the root 2. So it's going to turn back around somewhere along the way. And then it's going to... We're going to do a parabolic motif right there. It's the old touch and go right there. Just make it harmonize with the end behavior. There we go. And connect this one to the turnaround right there. Okay. So the graph is going to look something like this. And I'm just going to do the viewing window cutoffs because, again, I don't like to commit my answer that much. So I'm going to do something like this. So cut off the viewing window. Will cut those parts off. So cut off that part. And that'll be my answer right here. And we're good to go with this problem. Yes? Yeah. Our only job is to graph. And the graph is successfully done so right here. And just do a quick check, of course. We have this upwards, downwards behavior. And that agrees with this negative coefficient with an odd leading degree term. Yep. All 3 zeros are accounted for. 1, 2, and 3. And remember, this is a difference of 2 squares. It's not a rational square. This is not a nice square root, but it exists. So you should acknowledge it. Okay. And I think that's it for this particular problem. Next problem up, solve for the unknowns. We have a slight hark back to radicals. Alright, so we have cubic root of a squared over a to the power of negative 2 times square root of a. This is just for clarity. And then that is equal to a. Alright, so we're supposed to solve for the unknowns. The unknown is a. So make a few notes. A cannot be negative, and a cannot be 0. So on a side note, we have to say a is greater than a 0. We have to say that because if it's not so, it would cause this function, the square root function, to fail. So whatever answer we get, the answer needs to be greater than 0. Alright. So what's the optimal strat at this point? Well, Radical notation looks nice, but isn't super useful for crunching numbers. So let's change the radicals into fractional exponents. So cubic root is just 1/3. So we have a squared to the power of that radical is just 1/3. So just translations of radical form into fractional exponential form. And this one we shall let's pass it up. So this has a negative exponent. We can arbitrarily send it to the other side, thereby flipping the signage. So it becomes a squared. This one is just square root. So it's going to be a to the power of 1/2. So thus have we successfully transformed quotient in the start to quotient with fractional exponents equals a. So at this point, it's just going to be algebra involving exponential rules. So nothing too difficult. So distributive property of exponents. I'm going to drop the parenthetical after I distribute this 1/3 to this 2. We have 1/2 on the bottom. Might as well just should we distribute it? Yeah, let's just distribute it to the other side. So we're going to multiply a to the power of 1/2 to both sides. So it becomes copy paste that one, and then this one we shall multiply to the other side. So a bunch of a's. Be careful, don't just start willy-nilly crossing things out from both sides. Oh, we can, because explicitly stated here, we have to say a is greater than 0, because again, if a actually equals 0, then you have 0 in the denominator, which will cause this whole function to fail. So is it safe to cancel a from both sides? Yes, it is safe. But out of good habit, I'm not going to do that. Rather, I'm just going to consolidate these two, consolidate those two, and then move it over to the other side to make zero product property scenario. So again, technically you can start canceling out some of those a factors because we're assuming a can't be 0, but just follow good habits for now. If you're on a test, of course, obviously you can start. If you're pressed for time, then cancel them out, but you have to acknowledge a cannot be 0. Alright, but we're just condensing this for now. So this becomes a to the power of, we're matching the denominators, so 6/3. And then this one is, to match this one, we'll make it 2/2. And then all we have to do is summate the exponents. So 6 plus 2 is 8, keeping same denominator 3. Now that is equal to 2 plus 1 over 2. Alright, that is what we have. And again, some people will feel tempted to divide both sides by a to the power of 3/2. A to the power of 3/2. Which is fine, as long as you say a cannot be equal to 0, then you can do it straight off the bat. But let me subtract it from both sides. Let me move this one over to the left-hand side. So we're going to get a to the power of 8/3 minus that one. That is equal to 0. And then now we can factor out the lower of the two. So this is like 2 and this is 2 2/3. This is 1 1/2. So we can factor out a to the power of 3/2 from those two. So this one divided by itself is just going to be 1. And then this one divided by that one, you just have to do subtractive property of exponents. So we have 8/3 minus 3/2. Cross multiplication, we have 16 minus 9 is equal to 7 over common denominator of 6. So a to the power of 7/6. Alright. So again, this is the one we could drop as an answer. We have technically two factors, factor number 1, and then we have factor number 2. So again, just for completion's sake, I'm going to list both of them. So a to the power of 3/2 is equal to 0. Therefore, a is equal to 0. Here, that's a little more annoying to deal with. So we have a to the power of 7/6 minus 1 is equal to 0. So therefore, a to the power of 7/6 is equal to 1. How do we solve this? Well, you could just simply raise both sides of the equation to the 6/7 exponent, thereby yielding distributive property, a power 1, and then this one to that one, as equal to, that's just classic 1, and then we are done. So we have two candidates for the answers. We have a equals 0, a is equal to 1, but because we have this thing in the denominator at the start of the problem, a has to be greater than 0. So we're going to call that one extraneous, and we'll keep this answer. So it should be good, but let's do a quick test. Quick test for this one. So if we plug in 1, yeah, that's 1. If we plug in 1, that's 1. If we plug in 1, that's 1. So everything becomes 1, which is consistent. So 1 is confirmed. Good to go. So nothing earth-shattering right there. So again, there are some steps you can simplify along the way. Alright, next problem up, we have another radical situation. It's a slight detour into radicals. So we have in parentheticals cubic root of, what is this, b squared, quantity exponent 9, all over b power negative 4 is equal to 16 to the power of 5. Alright, so we don't need to do any log functions probably. Let's see what we've got. Well, we have this radical notation. We could use distributive property of exponent. We have this negative exponent. We could send it across. So I think that's going to be the plan of attack. So let us transform this one into fractional exponent first. So again, this part right here, this cubic root thing right here, we shall change that to 1/3 exponent. You don't have to explicitly write this step, but I'm just writing it for visual clarity. So we have, again, b squared to the power of 1/3, which is the radical, and then we have the exponent 9 on the outside. And then this one, because it has a negative exponent, we could just simply send it across the fraction bar right there. And once we pass it along, flip the signage. So b exponent positive 4, copy paste, right hand side. Okay, and then now we can use distributive property of exponent. So 1/3 of 9 is equal to 3. Thus dropping the first pair of parentheticals. Copy paste. Copy paste. Alright, so we have more distributive property of exponent. Distribute the exponent. b to the power of 6. 2 times 3. Don't do plus. Plus is when you're multiplying same bases. This is distributing exponent. Copy paste this. Alright, and you probably see where this is headed. Now that we have same base, now we summate the exponents. So b to the power of 10. Take a step back. We can't match the bases because we don't know what this is, but we can try to match the exponents. This is exponent 5. This is exponent 10. 10 is not coincidentally 2 times 5. So thus we can split this. Using exponential tricks, we have b squared on the inside raised to the power of 5, because again 5 times 2 gives us 10. And this is 16 to the power of 5. There we go. We have now successfully matched the exponents. They are odd exponents. So therefore argument of the fifth power is b squared, argument number 1. And then argument number 2 is 16. So we have potentially two answers when we take the square root of both sides. Be careful, because we're going to be transitioning from even-powered into odd-powered. So be sure to put the plus or minus 4. So again, we're applying square root to both sides. Transitioning from even power to odd power, so plus or minus. But don't be satisfied here. You need to double check your answers. So again, our two answer candidates are -4 and +4. Are these two answers safe? Within domain, we could plug in -4 into this b squared, because it's going to get squared, so the negative doesn't matter. But can we plug this one into there, right? Yes, we can. This is not a fractional exponent. Not a fractional exponent, so square roots will be, so the negative values will be eradicated. So this is a safe answer, and this is also a safe answer. So we'll keep both of them. And we're good for this problem. Wonderful. Alright, moving along, we have another problem, some more square root problems, or also cubics. So C, problem C, we have cubic root of C times fifth root of square root of C cubed and times cubic root of C power -2. So yeah, we love seeing functions within functions. That's always a fun time. Is equal to 3. All right. So what exactly should we do in this sort of situation? It just looks kind of gross, but I think if we just convert everything to fractional exponents, it should be fine. Yeah. So this one we shall transform into a fractional exponent, so c to the power of 1/3. And this one also change it to fractional exponent. And those ones also change to fractional. So let's do these two first. So this one, we shall change that to c to the power of 3 over 2. So let me just show my steps a little bit more. So that's the c cubed inside the radical, and then inside the radical itself is going to be 1/2 exponent. And then this one right here, same thing. We have the c to the power of -2. It's inside the radical, cubic root of 3. It's 1/3. Maybe I should color code this just a little bit. So this one is this 1/2. That's barely any different for the color. Whoops. So let's do this. That's the square root, which is 1/2. And then this right here is the cubic root, which is the 1/3. And this one is just going to be this one. I think that's fairly unambiguous. And then we have this fifth root. Let me get a little redder. Okay, so we have fifth root right here. That goes over the entire thing. So fifth root over the entirety. I'll represent that using the brackets. Okay, so that's what we get. We've just basically just transformed the notation, because fractional notation, in my opinion, is better for mechanics than is radical notation. But if you could do it in your head, that's perfectly fine. I just want to be clear for what's happening. So now we just have a bunch of distributive property of exponents. So distribute to that, distribute to that, and then we will distribute 1/5 to each of those afterwards. So copy paste. Distribute those nonsense on the inside, so we have 3/2 -2/3. They're being multiplied together, they are in the brackets, and they are being raised to the 1/5 power. Okay. So we have a few options. We can choose to distribute this one to here and to there, or we could just simply combine those two first and then distribute this afterwards. So I'm more inclined to actually put these two together. Yeah, so let's do that. Cross multiplication. So that exponent is going to be 9/6. And then this one is going to be -4/6. Inside the bracket still 1/5 out there, still c to the power of 1/3 right there. So I'm showing a lot of work but you could skip steps if you really want to. So 9 minus 4 is 5. What do you know? That's a nice number. Because we're going to distribute 1/5 to that one. Copy, paste. Copy, paste. Alright, so distributive property of exponent, we're going to get 1/6. Again, that's that one to that one. That's in the brackets, and then now we can free the brackets. It's going to be c to the power of 1/3 outside. And that is equal to 3. Okay. Well, we have multiplication, same base, so all we need to do is simply summate the exponents. So 6 plus 3 is 9. Oh, wait. Let's do common denominators. We'll do top and bottoms times 2. Yeah, to match it up. So it will be c to the power of, this is going to be 2 plus 1 is 3. Wait, is it that nice? That doesn't seem... I guess sometimes it just does end up being nice. So again, 1/3 plus 6 is going to be 2 plus 1 is 3. 3 over 6. Interesting. I didn't expect it to be this nice. So this is c to the power of 1/2 is equal to 3. So at this point, we can solve c by squaring both sides of the equation. Just be aware that this one does technically eradicate negative signs, but it should be okay in this situation. So distribute the exponent, we get c to the power of 1. Distribute the exponent, we get 3 to the power of 2, which is 9. So c is equal to 9, and then we should be good to go. But always double check. So we got c is equal to 9. Well, that's actually not very easy to check, is it? So we have 9 to there. We have 9 into there. Yeah, it's more hassle than it's worth. But I'm just checking the signage. So 9 is a positive value. It's okay to put it in there? Yes. It's okay to put it in there? Yes. It's okay to put it in there? Yes. So we don't cause any domain issues. So I'm going to say this is probably good to go. Good to go. And I'm too lazy. And this is kind of annoying to plug and chug anyway. Alright. Moving on to the last subset. Last problem of this subset. So we have cubic root of d times square root of d over 5th root of d cubed. That is equal to 5th root of 8. Alright, there you go. It looks like I've written it kind of funnily. Alright, so we could use the exact same strats as before. We can change everything into fraction notation, which is usually a nice way to go in my opinion, especially if you have multiple fractional nonsense. So let's change the insides first. I'm going to call this one the purplish one, and this will be the light purplish one. Yeah, so that's going to be d to the power of 1/5. You know, I'm going to start cutting corners just a little bit. So this fraction bar is 1/5. 1/5 times 3 is 3/5. So just be aware that this color came from essentially that one. So d to the power of 1/5 on the bottom. And then we're going to work with these two. Copy paste that one. Nothing exciting there. This one, however, exponent 1/2. And then we have the 1/3 on the outside. So all of that to the 1/3 exponent. Copy paste that. Okay. So we have a little bit of consolidating to do. So I recommend against distributing this 1/3 to 3 factors. So let us, since they all have the same base d, base d, base d, why not just combine these ones? So this is exponent 1. Just kidding, it's 2 over 2. So summate those exponents. We get d to the power of 3/2 all over this one. D to the power of 3/5. Copy paste. I'm being remarkably inconsistent with how I'm writing this. Okay. There we go. What to do, what to do. You know what? It's actually easier to distribute this exponent rather than just working with these straight up. So I'm actually going to distribute this to that exponent and to that exponent. So distributive property of exponents, we shall distribute 1/3 to this one. So 1/3 of 3 halves is just 1/2. So first distribution, this one to this one. And then second distribution of exponents, this one to that one. So it just becomes 1/5. So just be flexible, whatever works better for your brain, quite honestly. There we go. And then this one, we're going to do subtractive property of exponents since we have division. So it's just going to be 1/2 minus 1/5. 1/2 minus 1/5. Simple cross multiplications of 5 minus 2 over common denominator of 10, which gives us 3/10. So d to the power of 3/10 is equal to, I guess we have to change this one at this point. So that's 1/5 exponent. Alright, now let's take a step back. What do we have at this point? We have base d, which is unknown, so we can't match up the bases, but we can try to force exponential matchups. And this one, we do have a 5 trapped in the 10, so let's split the 3/10 into 3 halves times 1/5. Okay, there we go. In fact, we could probably mess around with the 8 as well. So 8, that's just going to be 2 to the power of 3, right? So we can take that 3 and multiply it to the 1. We will take this 3 and multiply it to the 1. I should have left this right here. That's okay. That's fine. So we have 2 to the power of 3/5. And here we can do a little bit of rearrangement. So you can multiply in any order you wish. So rather than have 3 halves, we can have 1/2 times 3/5. So 1/2 times 3/5. Because again, you can multiply in any order you wish, because 1 times 3 still gives us 3. 2 times 5 still gives us 10. Just be aware of potential domain restrictions. Because once you do this kind of trick right here, if d is actually a negative value, then this operation is technically illegal. But we'll check that afterwards. So now that we successfully match this exponent with that exponent, we shall group those two first. Alright. So since 3/5 exponent matches 3/5 exponent, we can conclude that argument of d to the power of 1/2 is equal to argument 2. Wonderful. So solving for d, we can square both sides. So d is equal to +4. And I think we're good to go. So +4, I don't think that's going to cause any domain issues, but we should always check. So d is equal to 4. So can we plug it in there? Yes. Can we plug that in there? Yes. Can we plug that in there? Yes. Okay, so domain check, quick domain check, it seems legit. And honestly, this answer does seem like an answer I would make. So I think we're good to go. Cool. That's it for the radical tangent. We have another problem right here. Solve for x. Straightforward solve for x problem. So we have x times 2x minus 1 squared is equal to 405. Wonderful. Okay. Well, off the top of my head, it doesn't look like there are any tricks for this particular problem. I think we just distribute. We're going to get a cubic, and then we're going to move this to the other side, thereby generating a polynomial situation, and then solve for 0 using synthetic division. I think we could kind of cheese this problem as well. Well, let me see if we could kind of cheese the problem. We have 405. It's divisible by 5, thereby getting 81, and then 81 is just 9 times 9. Okay, so I think that's how we can cheese the problem. Yeah, So you see how this thing is a squared, and then this is just exponent 1. You see how this is a squared, and this is exponent 1. So we could probably just do it like that, since the assumption that this is a nice problem, right? So again, kind of cheese strats is going to be 5 times 9 times 9. And we have this thing right here, which is just x, and then 2x minus 1 times 2x minus 1. Kind of situation, right? You can see how things kind of perfectly line up. So this one lines up with this one. But, you know, always double check to make sure it actually is legit. So if x is equal to 5, then this one has to be 9. Let's see if that's consistent. So 2x minus 1 question mark equals 9. So plus 1. And yeah, it works out since the numbers are assumed to be nice. So if you trust in your problem maker, you trust that your problem maker will give you nice numbers, then you could kind of cheese it in this particular fashion. All right, but let's use quote unquote more legit strats. Yeah, that's kind of cheesing the problem, but if we were to do this the long way, yeah, let's verify the cheese strat using the long. Well, actually, no, we technically already verified it, but let's just use long method. So binomial expansion, make sure you follow correct algorithm. So square that, it's going to be 4x squared, and then this one times 2. So that gives us negative 4x, and then negative 1 squared. Plus 1. So that's the quick binomial expansion for exponent 2. Alright, so we just distribute this x to each of those, and then we're going to move this over to the other side. So here we go. We're going to get 4x cubed minus 4x squared plus x. And then minus 405 from both sides is equal to 0. So yeah, standard factorization problem. We're going to factorize the polynomial, and then we're going to use zero product property. I don't think we can factor by grouping. This is a 4 and this is a 4 and a 4. This is a 1 and a 405. So yeah, that's out the window. So what are the factors of 405? Well, technically we already know. It's 5 times 9, right? Times 9. So obviously it's going to be a waste of time to list off all the factors. So I'm going to list off the smaller ones. So 1, 3, 5, 9, 15. I mean, technically we already know the answer, right? Factors of 4, 1, 2, and 4. Plus or minus. According to Descartes' rule of sign, it's going to be 1 sign change, 2 sign change, 3 sign changes. So we're guaranteed 1 positive real solution. At least 1, up to 3. Alright. So 3, 2, 1, 0. All terms are present and accounted for. So we'll populate the synthetic division chart. Algorithm. You know, since we already did the problem, let's just steal the 5. We know it's 5 already, so let's put 5 here. Drop the 4. Multiplication. Summation. Multiplication. What is that? 50 plus 30 is 9. Wait, 50 plus 30 is 80. 81. 405. Okay, that just basically confirms what we already did before. So we have 0 number 1, x is equal to 5, produces a 0 remainder. So therefore, this is a 0. Therefore, x minus 5 is a factor. This is leftover stuff. It's going to be x squared plus 16x plus 8, 81. Alright. Is this factorizable? That is the question, right? Do we have more zeros? Well, let me think. Let's use discriminant test. Yeah. See if it's worth our time. So b squared is 16 times 16. I think that's 256 if my memory serves correctly. If my memory serves me correctly. And then we have minus 4ac. So minus 4 times 4 times 81. That's a large size value relative to this one. So I think we're already overboard. Yeah, you see how this is already 16 times bigger than 16? And this is resulted from 16 times 16. So we technically didn't even have to do that because we have 16 16s, but here you have 16 81s, and we're subtracting those two, then the square root will be negative on the inside, so there'll be no real solutions. So this quadratic is not nicely factorizable. So therefore, this is the only factor, so our only valid real solution is x is equal to 5. For this situation, which again, we just confirmed what we've done using the cheese strats. Alright. So that's good. Long method verifies the shortcut method. So we're good to go. Do I want to do this problem? I don't know. It doesn't look particularly fun. You know what? Let's do it anyway. It's kind of more conceptual problem, I guess. So unfortunately, I do need to waste time writing it out. So we have r of x and what is that? T of x? Yeah, T of x. Our square root functions. I'm just going to shorthand. That's not square, that's function. I mean, that's square root. So r of x and t of x are square root functions on the xy coordinate plane. What else is there? For numbers a and b, alright, so this is the premise. Then as a subconditions, we have numbers a and b. So for a and b, which are real numbers. Constants, let's say. For a and b, which are constants, a is greater than b. I think there's some more conditions as well. Hold on, let me see. For numbers a and b, where a is greater than b, we have also r of a is less than t of a. And then we are also told that r of a, oh, this is kind of annoying. What have I done? So we have r of a is less than r of b. I should have just skipped this one. And there's one more thing. Wait, there's more. And then we have t. Ooh, it looks like f. And then we have t of a is greater than t of b. Wonderful. Is that it? I hope that's it. For how many solutions does the system of r and t of x have? Wait, what? Okay, hold on. Let me... Alright, so the question asks, how many solutions does the system of rx and tx have? I'm not even sure if this is grammatical from a mathematical word problem viewpoint, but hopefully it makes sense. So how many solutions does the system of r and x and t of x have? That's a lot to write. Oh my goodness. My word. Alright. R of x and t of x are square root functions on the xy coordinate plane. We have a and b, which are constants. I can't spell correctly, apparently. Constants. Let's move that over. There we go. So for a and b, which are constants, we have fact number 1, a is greater than b. Fact number 2, r of a is greater than t of a. And then fact number 3, r of a is less than R of B, and then we have T of A is greater than T of B. Okay. How many solutions? Oh, okay, so I think this is just a visual problem. We'll just do a rough sketch, and then we'll visualize the situation. Alright, so what do we have? There's some sort of arbitrary x. There's going to be the x-axis. I don't know where to place the y-axis. It could be here, it could be here, or it could be here. But it's not important. We just need to know above the x-axis will be positive y values, and then below the x-axis will be negative y values. So for some arbitrary a and b values, which are constants, we have a is farther along the x-axis to the right, and then we have b, which is closer, which is smaller than the a value, because that's given right there, summarized right there. Okay. And then this one doesn't seem super useful at the moment, so I'm going to use this one first. We're told that r of x and t of x are both square root functions, and those ones behave very typically. So for square root functions, you have this one, it's going upwards, or you have downwards, or you have backwards, or other backwards, right? So we have 4 motifs. We can have motif number 1, we can have motif number 2, we can have motif number 3, or motif number 4. Because we're told nothing else, unfortunately. Okay, but we'll try to stay consistent at least. So we're trying to figure out stuff with the r of x function. We are told that r of a is less than r of b. So it's a declining function. So it can't be this one, and it cannot be this one, right? Because if the b value is here, it leads to a y value up there, and then if we have the a value here, it leads to a higher y value, which is not what this one is saying. It's saying that the later y value is less than the earlier y value. So again, it's a declining function. So not this one and not this one. So we either have this one or that one. But at this point, it's kind of ambiguous. So from this clue alone, r of x could be this one. I'm sorry, it could be this one, or it can be this other motif, right? Yeah. So we don't know which one it is, unfortunately, from this clue alone. So we're just trying to piece together what's going on. So we have t of a is greater than t of b, so the later y value for t of x is greater than the earlier y value for t of x, because b comes earlier than a. So this is going to be doing opposite of what the r of x is doing. So it's going to be increasing over time. So from this clue, t of x could be going upwards like that, or it could be going upwards like that. Again, we don't technically know which one's which. Okay, and then of course we have this one right here. R of a is less than t of a. Well, so those are 2 candidates, and then those are 2 candidates. So what are we told for? What do we get from this piece of information, right? What is this nonsense? R of a, so here's going to be a arbitrarily, okay? So R of a is less than t of a, which is like right here-ish. So that means that this one at some point is below this other one, but we have many combinations, right? So R of x, it could be doing something like this, right? So if we assume this is R of x, and if we assume that this is t of x, then putting these 2 pictures together will get us something like this. So that will mean that they have 2 solutions at one point. They were guaranteed to intersect at one point, given that this thing is true. But that's not the only scenario we can possibly have, you understand? It could be that we have this scenario, right? So in this case, if we have this scenario, then this y value for r of x is less than this y value. So we're still guaranteed one solution right there. Still, okay, so we still have one solution right there. So given either of these two scenarios, if we assume this is true for graph t of x, then we're guaranteed we have one solution regardless of the situation. But is that true if we have this scenario, right? Is that true? Let's... I have a feeling I'm saying something wrong. Okay, that's fine, that's fine. Let's assume... Oh, I think I know. Okay. We don't know the shiftings for these ones. And they don't go indefinitely. Okay, well, I think this is a poorly designed problem. I think it's too ambiguous, honestly. So it might be a waste of time. Okay, so I changed this from the original problem. This one, I reworded it to square root functions. But on my original paper, it just said radical. It's a kind of an ambiguous radical. Right? But let me keep it the way I changed it. So let's keep it as square root functions. So I think we are not guaranteed any solutions because we're not informed of any shifts. We don't have enough clues. Because there aren't enough clues for the situation, we don't necessarily know where overlaps can potentially occur. So let me explain that. So let me just show you a situation. So let me show you on a different layer. Let's draw a red graph. It's going to be something like this. And again, this is assuming only square root functions, which have a domain restriction. The inside here has to be 0. It has to be greater than or equal to 0. So whatever's inside here, if we call that x, then the x input must be greater than or equal to 0. So we have this clear anchoring point right there. Okay, and if you have another square root function, let's say it's x plus 1, right? So this is just a shifted version of what this one is. So in that situation, it would just be something like this. But according to the problem, they're going to be opposites of each other, right? So for the problem that we're doing, one of them is going to be doing something downwards like so. Put it on a different layer. So something like this is going to be the negative square root of x, for example. So again, this b value leads to this smaller y value than does this a value, which leads to this one. I think that's confusing. Let me write that down. So again, if we have an a value, if we have a b value right here, it leads us to this y value, which we call it, what was it? T of x was the top one. Okay, so this is t of x, this is t of b. And this is an a value, it leads to a higher y value, t of a. Wait, is that right? Yeah, t1 is the growing function. And then the r of x is the shrinking one. So this b value leads to that particular y value, for example. So this is for r of b. And you can see that this is a higher y value than is this y value, which is basically r of a. Okay, so that's what we can sketch out, right? But here's the thing, though. If you take this one and then you just think about what could potentially happen, you can create a situation where it is true. So for instance, like, oh no, they have the same b and a values, right? Okay. Let me, So let me just do it like this. So for all we know, this blue function could be shifted over like so, right? And it could be shifted upwards like this. And then let's deliberately force a non-intersection. So if we have the red function currently where it's located, anchoring point at 0, 0, if we move this one like right here, for example, and we just put it right here, so we can see that the blue function terminates, it has the anchoring point right there, right? Right here. So can we satisfy the situation? Yes, because right here the r of b is indeed greater than r of a. So we can see it right here. So this is if we input b into our r of x, it leads to this y value, and then if we input a into r of x, it leads to this lower y value. So that would satisfy this particular condition. Yeah, so that satisfies this one. But you can see that we've deliberately created a situation where they don't intersect right here. So how many solutions does the system of r of x and t of x have, given these pieces of information? I don't think they're guaranteed any solutions. So thus, we can say 0. We're not guaranteed any solutions. How do you spell guaranteed? Guaranteed? That looks weird. Not guaranteed any real solutions. Yeah. Simply because I don't think there's enough information for this problem. So, unless I'm missing something. Yeah, I'm going to stick with my answer. So again, we don't know the shifting for the blue function nor the x function. So I can deliberately design a situation where they have no intersections, but all 4 of these conditions are satisfied. So because we've satisfied all 4 conditions, but they don't have an intersection, then we've falsified the idea that they're guaranteed one solution. So they're not guaranteed any real solutions. And I think that's satisfactory enough. So I should have just skipped out on this problem, honestly. Okay, but let me clear it. I felt like that was not worth the time because we're not guaranteed any real solutions. But sometimes I guess you do end up with such situations. And that's okay. Next problem up, we have two functions yet again. So we have f of x. This is a new problem. F of x is equal to some quadratic. It's going to be 3x squared minus 12x plus 16. So that's the quadratic, and then we have g of x. That is equal to a of x plus 8. Where a is an integer. Interesting. As an integer constant. I should just put that. So I'm trying to specify that x is a variable, and then this one is not a variable, it's a constant. But where a is an integer constant. Is this even an adjective? I don't know. Integral. Something like that, right? I'll just put in parentheses constant. Okay. So again, I'm just trying to say that this is just a fixed number, which is a constant, and then these ones, the x is just the variable. So this is not like a double variable situation. In other words, g of x is just a linear function with a slope of a, and then we have the quadratic function f of x right there. So that's the setup anyway. So we are told that f of x and g of x intersect at the vertex of f of x. Determine the value of f of a. Okay. So given this particular situation, then they intersect at the vertex. So how do I write that in English? F of x and g of x intersect at the vertex of f of x. That sounds really weird. Sure, and then we are asked to determine the value of f of a. Some more strangeness. Alright, I think that's all we need. Yeah, that's it for the setup. So again, we're given some sort of quadratic equation, we're given some sort of linear function, a is an integer, and we are informed that the vertex of this one is intersected by this one right here. Okay. Are we in anything else? That's interesting. Okay, so I think we just need to determine the vertex of f of x. So find the vertex of f of x first. It seems to be the most straightforward thing to do. So, which is review, right? So make sure you slap on those parentheticals and then factor out the 3 from term number 1 and then term number 2. So let's do that. We're going to factor out just the 3. Don't factor out 3x. Just the coefficient. So we have 3 times x squared minus 4x. So basically a brief review of completing the square situation. So to complete the square, it's going to be x minus 2, close parentheses squared times 3 amplitude. But we need to have a correcting value outside. So here's how we do it. This is going to be 2 squared, which is 4. 4 times 3 is 12, so we have to minus 12. Yeah. So minus 12 is going to give us plus 4. And that's it. I've skipped some steps for the situation, but you could use your favorite, whatever algorithm you like to use for completing the square, just use it right here. Okay. So just to double check real quick. So again, negative 2 squared is positive 4. Positive 4 times 3 is 12, and then 12 plus 4 takes us back to 16. So this is correct. So the vertex of that is 2, opposite land, right? So what number minus 2 gives us 0? It's positive 2. And this number is just 4. Copy paste. That's the vertex. And again, we derived that from vertex form of f of x to get this. Covered in previous streams. Alright. So that's that, and we are told that this linear function intersects f of x at this location, which means that if x is 2, then y value is 4 for that particular function. So let's just plug it in. So plug in y value is going to be 4, and then x value has to be 2. And let me just color code that just for visual clarity. We're going to call this as orange 2, orange 4. That's the vertex for that one, but it also works inside here. So that's the 2 for the x value, and then the 4 for the y value. So this is a single variable, single unknown. Therefore, a is solvable, right? So minus 8 from both sides, we get negative 4. Divide 2 from both sides, a is equal to negative 2. Alright. Is that all we're supposed to do? Oh, no. Okay. So what's the question asking for? Determine the value of f of a. We have the a value, so we're just going to plug that into f of x. We don't even need to generate the equation, so that will be superfluous. So if you write the negative 2, if you take this a value of negative 2 and put it here, that's nice. You get the linear function g of x, but that's not what the question is asking for. It's just asking for f of a, which we already know. So this is a waste of time. So take that negative 2 and plug it into the old f of x. Alright. So fairly straightforward. Yeah. Okay. I was thinking if there's a shortcut, but off the top of my head, there's no obvious shortcut. So we're just going to plug in negative 2 into f of x. So f of negative 2. So we have 3 times negative 2 squared minus 12 times negative 2 plus 16. Alright, spacing is a little bad. Let me move it over just a little bit. So again, we have plus 16. Alright. So we just need to crunch the numbers. It's not too terrible. So 4 times 3 is 12. And then this is plus 2 12s. That's a plus of 16. Hey, that's some nice numbers. This is going to be 40. That's going to be 52. So f of negative 2 is equal to 52. Because remember, the a value is negative 2. We found that. And once you crunch the numbers, you get 52. And that should be our answer. So determine the value of f of a. That's simply 52. Should be good to go. Yeah. If you want to have extra... no, that's it. That's it. There's no other way to check it off the top of my head. Yeah. Okay, we should be good to go for this particular problem, yes? Yeah, nothing else. Alright, so that takes care of that goofy problem. What else do we have? Okay, moving on. We have another radical problem. It's not that difficult, though. It's strictly square roots only. So we have square root of x plus 6 plus the square root of 10x plus 6. So that's how you make problems look more complicated. You just put functions within functions to try to intimidate people. Well, you know, just one piece at a time. So we have square root function, so we can open up by doing square roots, applying square root function to both sides. So we're going to square left hand side, and then we shall square right hand side. So I'm going to symbolically represent it like this, but just applying square to both sides. So applying square to the right hand side, we will negate the square root, freeing the inside right there. So we're going to get square root of x plus 6 plus square root of 10x plus 6. And then of course the right hand side, make sure you square this right hand side as well, so that becomes positive 36. So we have a classic square root plus square root equals constant value. So what we need to do is we just need to square 2 more times to undo the square functions. But is there an optimal way to do this? Not really. So let's just apply the square root yet again. Some people will opt to take one of these square roots and move it over to one side. You can do that, but honestly, it's going to result in the same thing, so it doesn't matter. So let's square both sides again. But be careful. This one, I'll show you the wrong answer. Don't do this, okay? So that is improper distribution. This is a binomial expansion. Yes, you will get this term, because this one squared does in fact give us this, and this one squared does in fact give us that one. But you're missing the middle term. So let me scooch this over just a little bit right there. And then we acknowledge that we're going to have to do this one times this one times 2, following the algorithm for binomial expansion. So be careful. This is where people can potentially slip up. So again, it's going to be plus 2 times this one times this one. And since they both are inside just generic square root, we can combine them together in totality. So this one has another distribution to take care of, which is kind of annoying. So we have 10x times 10x, which is 10x squared. We have 60x plus 6x, so that's just going to be 66x. And lastly, we have 6 times 6. There we go. Is this nice? Not particularly. But we can start consolidating like terms. So let us combine those two. Let us combine those two. Copy paste this nonsense. Of course that one. This one I'm going to just try to leave it alone. That's kind of a doozy, honestly. Alright. Moving forward, can we do anything else that's easy to do? Well, we can try to force everything over to right hand side and keeping the square root. Isolate the square root so we can square it. So we're going to move this to that side, move this to that side, and then divide both sides by 2. I really hope I'm doing this correctly. It doesn't look like it's going to end up nice, does it? That's okay. So we have square root of 10x, let me put the 2, plus 66x plus 36. Again, subtracting that from both sides, subtracting that from both sides, we're going to get, I really don't want to do this. Okay, so it's going to be 336 squared minus 12, and then minus 11x. Alright, but it looks like we have to in order to divide by 2, right? So let's divide both sides by 2. So we're going to get square root 10x squared plus 66x plus 36. Alright. Divide by 2. So we have to divide everything by 2. So this is going to be divided by 2. But be careful about how you do this, okay? It's technically 36 times 36. We're only dividing by 1, 2. So only one of those 36's gets divided by 2. So therefore it becomes 18. This one divided by 2, 6. That one divided by 2 is unfortunate. There we go. And then now we ask ourselves, do we want to suffer and square both sides of the equation? Well, we don't have a choice, do we? So we shall square left hand side and we shall square right hand side. Okay. But you know, there are some tricks we can perform. This one, can't we combine them? Yeah, I'm going to combine them, but I'm trying to combine this without fully doing 36 times 18, because that's annoying to do. I don't have a calculator at the moment. So this 18 is just going to be 3 times 6, right? And then we can just multiply those two together first. So 36 times 3 is a little bit more doable. So that's going to be 108 of these 6's. And we're going to be removing one of those 6's. Whoops. Yeah. So since we have 108 6's and we're taking away one of those 6's, then we have 107 of those 6's left. So I'm trying really hard to avoid having to multiply that out. Okay, so this is the thing that we're going to be squaring in the aftermath. So we're going to square this. So we can successfully cancel out the square root, but we're going to copy paste the argument since we're squaring both sides. That's what we get. Oh, this is going to be really bad. Did I even do this correctly? Let me see. Let me see real quick. Yeah, this is generally unpleasant. I have a feeling we could just cheese this problem, right? You know what? Let's think about this for a moment. So can we just cheese this problem? What square root of what plus square root of what gives us 36, right? So 36 consists of 18 plus 18, right? So we can just start moving things around. Again, in an attempt to cheese the problem, to square root. Let me think about this. Square root of something plus square root of something gives us 36, right? What are some nice square roots? We have a 9 and 25. Nope. Okay, well, I'm pretty sure we could cheese the problem, but let's continue on legitimately, right? So we can, this is really annoying. So we can apply the squaring to binomial expansion right here. So this one's going to get squared. Ooh, that's disgusting. So that's going to get squared. Following the algorithm, it's going to be this one times 2. So the 2 will clear the fraction, right? So thus we will get negative something very nasty. 6 times 11 times 107. Again, this 1/2 is cleared by times 2. Alright, and then we have this one squared, which is going to be plus 121 over 4x squared right here. Okay. That's really bad. That is really bad. Okay, well, it just ends up being like a simple quadratic. Well, not a simple quadratic, kind of a nasty looking quadratic, but it's doable. We can resort to quadratic equation afterwards, after we clean up this atrocious mess, right? Okay, well, this is not going anywhere. That's just really bad. And then this one is also kind of bad. But what choice do we have? Yeah, that's really bad, right? Okay, well, let's just start moving things over to one side. So I'm going to move everything over to right-hand side. Yes. So this is basically, this one right here is basically 40x squared over 4 to match the denominator. So if we subtract 40 over 4 from this one, we're going to get 81 over 4x squared. So let's start crossing things out. Satisfaction of crossing things out. Then we're going to subtract 66x from both sides. So minus 66x and then minus 66x. Hey, look, that's a 66, right? Okay. At least that's not too bad. So we have, I'm going to combine these two to make 66 of 107 x's. And we're going to be taking away 1 66x. So that's combined. That's nicely combinable. So this one is taken care of, and this one's almost taken care of. And then lastly, we have minus 36, and then minus 36. Hey, we can do partial distribution, right? So this one is going to be plus 107 squared times distributive property of exponent 36. And you know, we can take away 136. Okay, so it's looking a little better, but still kind of bad. So there are no more x squares. So just we have 81 over 4 times x squared. Don't forget the 0. And then here's where the magic happens. We have minus 107 of 66 x's, and then we're taking away 1 of those 66 x's. Since it's negative and negative, we can consolidate them, and therefore we have a negative 108 of 66 x's. So that's gone. Here is also the same phenomenon as well, but oh, this is bad though. This is a bad number. Okay. It's going to be, here's how I like to think about it. This is 107 squared times 36, and we're taking away 1 of those 36's. So in effect, that becomes plus 107 squared minus 1 of those 36's. Okay. Brilliant, right? Well, this is what we have, and it looks, quite frankly, very awful. Do we have real solutions for the situation? It's honestly kind of a mess. I think we do. Let's just multiply both sides. Let's clear this fraction first, right? Well, understand that at this point we have a quadratic. So we can use whatever algorithm we wish to solve for this quadratic. The only question is it a nice quadratic? At the very least, we could start to simplify a few things. This term here has factors of 3. This disgusting term also has factors of 3. And then this term here also has factors of 3. So at the very least, we can start to clean things up just a little bit. Alright? So let us at least try to do that. So if we divide this by 3, it becomes 9 times 3, which is 27. Yeah. This one is divisible by 3, so that's going to be 22. This is divisible by 3, so that is going to be 12. Can we do more than that? This is also still, this is divisible by 3, this is divisible by 3, and then this is divisible by 3. So we can clean up just a little bit more. So divide by 3 is 9. And then divided by 3, I'm trying to avoid multiplying as much as possible. Divide by 3 is 36. And this one divided by 3 is 4. So can we do more than that? I think that is all we can do. Alright, So let's do a little bit of cleanup just to see where we're at. 9 over 4 times x squared. Okay. And then minus an unfortunate 36 times 22x. And then this nasty. This is like the nastiest one, honestly. That's a yikes. Okay, well, I just wish to reiterate, this is just a quadratic, but the numbers are just awful, awful, awful. So you know what? I'm going to cheat, because honestly, the rest of this is just trivial. So what I'm going to do is I am going to go to my calculator, and then I'm just going to input this into the calculator and see if it's at least worth the time. You know what I mean? Okay. So we have 9 divided by 4 times x squared minus 36 times 22x, and then plus 107 squared minus 1 times 4. All of that is equal to 0. Let's see what the calculator says. Okay, it's bad. It's awful. Alright, which means that I probably goofed up somewhere along the way. Interesting. Well, all this work for what? I don't know. I don't know anymore. Okay, well, in summary, this one is a quadratic. Slam dunk that into the quadratic equation, but the numbers are really bad, and that implies that I may have messed up somewhere. So let us take a quick review. We'll see where things have potentially messed up. Well, I guess first let me just input the actual problem into the calculator. We'll see if it's even worth, we're gonna see if it's even worth doing this problem. Like maybe I just designed this problem poorly, right? But at the very least, if we square both sides, so we're basically just starting over at this point, unfortunately. So VOD watchers could easily skip over. I'm just gonna not timestamp the previous situation. So squaring both sides, we get to this particular form. Yeah, I don't know what exactly where things had gone wrong, but here we go again. We have this one right here. So maybe it's better to move one. I want to move this one over to this side. So let's see if that actually makes things a little easier. I think we're still going to get some nasty numbers though. So we're going to get 36 minus square root of x plus 6. There we go. And then we're going to square both sides. So we undo the square function, so we get 10x plus 6. Make sure to worry about domain afterwards, of course. Okay. So we still get the very nasty 36 times 36, but I'm going to leave it unmultiplied for now, because we might have simplification opportunities. It's going to be this one times 2 following algorithm. And then this nonsense squared. Number 1, the negative gets squared, so it becomes positive. And then number 2, it's going to be x plus 6. But since everything is positive, we can just drop parentheticals. Alright, so we have the situation right here. It actually looks nicer than what we had before, right? So we can cancel 6 from both sides. And we're going to move the x over, so it becomes 9x. And then we will move this one over. No, this one we're keeping on that side. And then this is what we're going to move over to the other side. So minus 36 times 36 equals leftover this nonsense. You know what? It actually looks a lot nicer than what we had before. Everything seems to be divisible by 9. So this term can divide by, we can factor out the 9. We can factor out 9. We could factor out the 9, so why not do it right now? So factor out the 9, and then factor out 9 from one of those. Not both, only one of them. And factor out 9 from that. Why does this look so nice now? Okay, well, And then now we can simply square both sides of the equation. So don't forget this is a binomial, and then this is going to be okay, I guess. So squaring this nonsense. X squared, this one times that one times 2. So it becomes negative. I'm going to do this one times 2. Okay, just following the algorithm. And then lastly, we have this thing squared. So negative squared is positive. This one's going to get squared. That one's going to get squared. But I'll leave that one alone. Like that. Square this nonsense. So this is where you should be careful with your parentheses. So first we square the negative 8, thereby getting positive 64, and then we got to square this one. But leave them in parentheses, please. That's what we get. So can we simplify things at this point? No, because this one has no other factors. So unfortunately, we have to deal with this nonsense. So let us start freeing things up. So this one I'm going to leave it as 8 times 36x. I'm going to leave that as 16 times 36 squared. This is nasty, of course. Yikes. So 64 times 6. Alright. And we shall move everything over to the other side. So can we do some simplification stuff? Yeah, I think we can. So keeping those together, we have, is there an 8 trapped in there? Yeah, wait. This is 4 times 9. Okay, not the best. So I'm going to start breaking this up. So that's 4 times 8 times 9. Again, I'm just trying to avoid punching numbers into the calculator. You don't have to do it. I'm just suffering here. So minus and then 64. That consists of 4 times 4 times 8. Kind of see what I'm doing, hopefully. So this has been moved over to right here. I just broke up the 64 into 8. Wait, that's 16. Why? Times 2. Yeah. So 2 times 4 is 8, and then 8 times 4 takes us back to 64. I just basically broke this up. So that's already broken up. And then here we have that one minus this one. So again, I'm just trying to avoid using calculator as much as possible for no real reason, honestly. This one consists of 16 times 4, just to match them up, times 6. There we go. Okay. All that is equal to 0. So this one we move to the other side by subtracting it right here. So that's gone. Okay. Let's take a step back. This one is by itself. No problems there. This one is combinable with... I'm going to put an X. This one is combinable with this one, right? Yes. So how do we do this? We have that thing which matches with that thing. So all we need to do is combine the coefficient, which is 9 and 2. So that's 11. So we have minus 4 times 8 times 11x. So this has now been combined with that one. And then here, this is really unpleasant. Is there a way around it? No, there isn't. So if we conceptualize bringing these two together, it's going to be 36 squared minus 24. Of those 16s, yes. So in parentheses, 36 squared minus 4 times 6. Close parentheses of those 16s. Is that worth it? Maybe not. Okay, so we still have this nasty quadratic situation, and it honestly looks terrible. But I think I'm just going to put it in a calculator at this point, because it is a big waste of time. Yeah, I think I just simply messed up writing the problem. Alright, so I'm up to the minus 24 times 16. And that is equal to 0 in the end. I hope this works out. I really, really hope it works out. And it still doesn't work out. We still have irrational numbers. Okay, so this is just a poorly designed problem. So long story short, this one does have a solution, but it is not a nice solution. Yeah. All right, last resort. I'm just going to plug this in directly into the calculator. I'm going to plug in line 2 directly into the calculator, and we'll see if it actually works out. So I'm putting in x plus 6 to the power of 0.5 plus parentheses 10x plus 6 to the power of 0.5. And that's equal to 36. Let's see if there's actually a nice solution. Yeah, there's no nice solution. It's irrational. It's irrational. There is at least one solution. I think there's only one real solution, but it's an irrational real solution. All right. So that's a kind of a waste of time. So in conclusion, for this particular problem, it's definitely doable. It's just that we get to a quadratic situation where there's no nice algorithm to do it, so we just plug it into a calculator. And there are two solutions. One of them will be extraneous, and then the other one will be the actual solution, which is irrational. Yeah. So if we get a negative argument, then we have to exclude it. So I think that'll be it for that particular problem. And then let's see how many more we got. Oh, it's actually quite a bit. Okay, let's do one more for the road, and that'll be it for today for this session. So we have 2 to the power of 6 is equal to 4 log base 3, because I do want to hit this log problem, and then we have 3x squared. All right, so classic situation. We have base 2, we have base 4, you know. Can't we get this base to match that base? So let's, or rather, can't we get this base to match this base? So it doesn't matter which way you do it. I'm going to manipulate this side. We can get 2 to the power of 2, in parentheses, power of 3. Alright, so that's the plan of attack. We can easily change this to base 2 as well, but let's just do this one. So again, transforming this into base 2 to the power of 2, parentheses, power 3, because 3 times 2 gets us back to 6. Copy paste this other side. Alright, so since we have successfully matched the bases, this is base 4 to the power of 3 is equal to base 4 to the power of log of base 3, parenthetical 3x squared. Drop the base. So we have these two are equivalent. So 3 is equal to log base 3, 3x squared. Alright, looks pretty good. We can simply exponentiate both sides. Or you could just do the simple one. Log base to the power of this equals that. Yeah, let's just do it like that. So base 3 to the power of 3 should be equal to 3x squared. Perfect. So we'll divide 3 from both sides. Watch out for plus or minus if we take the square root of both sides. We get x is equal to plus or minus 3. But make sure you check for extraneous solutions. Are both answers valid? Yes, because we have a square here which will eradicate negative signs. So keep that solution and keep that solution. So both solutions good to go. That was so much faster than the previous problem. But it is what it is. Alright, we have one. Let's just keep going until my roommate starts telling me dinner is ready. So we have, next problem, 48x squared times x squared minus 1 is equal to 9x squared. Oh, I'm sorry, just 9x times 4x squared plus 1. So what are we supposed to do? I think we're just supposed to solve for x. Alright, so there's an opening move that we could potentially do. We can try to divide x from both sides, thereby getting this one. But once we divide x from both sides, we acknowledge that we might be missing an answer. Alright, so x could be equal to 0, right? So again, I'm going to skip that. I'm not going to do that. I'm just going to use distributive property. But be aware that yes, you can cancel 1x from here, and you can cancel 1x from there. But you just acknowledge that to do that move specifically, x cannot be 0. And besides, we don't want to lose an answer anyway, potentially. So I'm just going to distribute this to those two, and then distribute this to those two. So probably resorting to synthetic division in the end. So this one to this one. 48x to the power of 4, distribute that one. Yeah, there's no factor by grouping that I can see. So that's left-hand side, and then right-hand side distribution. This one to this one gives us 36x cubed. That one to that one gives us 9x. Alright, and I'm going to move everything over to left-hand side. So we're going to get 48x to the power of 4 minus 36x cubed minus 48x squared minus 9 from both sides, 9x from both sides, equals 0. Alright, so that's what we're going to get. As you see, all terms have an x factor, so we can bring it out. Can we divide this by 3? Yes, we can. So let's divide... Wait, can we? 8 plus 4 is 12. 12 is divisible by 3. Yeah, so let's factor out 3x from everything, just to make the numbers slightly nicer. So we have 116x cubed. We have 12x squared. We're going to have, steal the work, minus 16x. Divide by 3 is minus 3. So that's nice. So we have this particular scenario. It's cubic, so we're guaranteed one answer according to Descartes' rule of sign. There's one sign change, so we have one positive real solution for this polynomial bit. So let us do that. So 16, negative 12, negative 16, negative 3. What's our 0 candidate? Let's see. So factors of 3, 1 and 3. Factors of 16, 1, 2, 4, and 6, 8, and 16. We're going to pick the lower numbers, of course. I think we can choose 1. Or maybe 1. Let me think. Maybe 1/2. Yeah, let's choose 1/2. I think 1/2 is going to be good. So 1/2 times this one, drop the 16. Half of that is 8. Summate is negative 4. Half of that is negative 2. Summating is negative 18. Huh. Did I botch the sign somewhere? Let me double check. No, signs are correct. Okay, so it's just a very unfortunate situation. So this is negative 9. Alright, so 1/2 did not quite work out. Why not? Because this needs to be positive. So this needs to be larger sized. So this one needs to be larger. Okay, so 1/2 is not a good choice. Alright, so let's pick something larger. Let's pick 1, positive 1 instead. And then maybe we can use intermediate value theorem. So 16. Multiplication, summation is 4. Multiplication is 4. Summation is negative 12. Not quite still. Interesting. It's still negative value. This is still negative. So we need to pick a larger value. Maybe. Let's pick 3. I feel like that's too much. I'm just wild in here. So this is going to be 48. It's going to be 36. Yeah, that's too big. But let's see what happens, okay? So 108 8, which gives us a big positive. 3 times a big positive is even bigger positive, which is even bigger positive in the end. Which means we have a 0 between 1 and 3, according to intermediate value theorem. So what is between positive 1 and positive 3? 3 halves, right? So let's try 3 halves. It better work. I think I've been having a string of bad luck for the synthetic divisions. Probably because I don't have a better algorithm. But this should work. So let's drop that. Product is 8 times 3 is 24. Summation is 12. 6 times 3 is 18. And then summating that is positive 2. Hey, it finally worked. Good. Good stuff, good stuff. Alright. So that means that that's a 0 since it produced a remainder 0, which means factor is x minus 3 halves. These are divisible by 2. So we have an 8x squared, we have a 6x, and then we have a 1 right there. Let's transfer this one to that one. So thereby getting 2x minus 3. Don't forget the original 3x on the outside. That's very easy to forget about. Now this should be a factorizable quadratic, right? Is it? Let me think. So discriminant test. B squared minus 4ac. Yeah. Oh, it's a very nice one too. Okay, good. So this one is a factorizable quadratic. So it's going to be 4 and 2, 1 and 1. Yep. 4 and 2, 1 and 1. 4x and 2x and 1 and 1. All signs are positive. Okay, so that should be fully factored form. Let's just do a quick spot check. So that's going to be multiply all of those for the partial distribution. We have 3 times 2 times 2, which is 12. 12 times 8 is 12 times 4 is 48. X power 1, 2, 3, 4. Yes. So we have 48x4, 48x4. So that seems legit. And check the constant as well. 1 times 1 times that is negative 3. Yeah. Okay, so that seems pretty legit. Yes. Yeah. Okay, so I have great confidence this is correct, but now we just need to solve for them. We have multiple answers. So we have solution number 1, which is negative 1/2. We have solution number 2, which is negative 1/4. We have solution number 3, which is 0. And then we have solution number 4, which is 3 halves. So 4 solutions for our situation. So for this thing, we have those 4 solutions. And polynomials, the domain is all real numbers. So all the solutions are valid. So we're good to go. Alright. And I think that is going to conclude it for now. Wait, should I do one more log? Oh, you know what? Let's do one more log problem. I'm sorry. This will be the final problem. I do want to hit 2 log problems, and that should be good enough. Alright, so we have log problem. What is it? We have log base 10 of 5, and then that's going to be times log base 5 of 10. That's kind of goofy. And then we have log base 50 of x plus 5. Alright, so we have multiple types of bases. We have log base 10, we have log base 5, and we have log base 50. There's no log rules where you can just combine this, okay? So don't do, oh, 10 times 5 is 50. We don't have an algorithm for that, at least to my knowledge. So what can we do for this situation? Well, we can do change of base. We can try to get everything into either log base 10, log base 5, or log base 50. And I don't think it matters which one we do, right? So I'm going to arbitrarily select log base 10. So this one is already in log base 10. This one we can change into log base 10 of 10, over log base 10 of 5. Now, you know what? That's actually the good strat. Lucky strat, because it matches. Okay, and then this side we can, you know what? We can just leave it as is for now. We could always change it later, right? So that's what we have. So we can see that log base 10 of 5 cancels with log base 10 of 5, leaving us with just that. Hey, in fact, isn't that just 1? Perfect. Some days are luckier than others, or some problems are luckier than others. Okay, so we have 50 to the power of 1 should give us x minus 5. So 50 to the power of 1, which is just 50, should give us the argument. So solving for x is equal to 45, and we should be good, right? That was very fast. So we have a positive number in here. The whole argument becomes positive, so that's a valid answer. No other domain checks? Nope. So this answer should be good. And I think I'm happy with now. So let's conclude it. I'll probably be on maybe a little bit later. Maybe probably do some English grammar, but I think that's good for now. So I'll see you another time. Yeah, have a good one.